So thank you, Danilo, for the introduction. So in this first talk, I just would like to show you why we need a lot of flexibility in today's Internet of Things systems, and more specifically in the wireless sensor nodes that are a sub-part of the IoT. So if we have a look at Internet of Things, there are a lot of things in Internet of Things. There are smart devices, there is the cloud, there is the network, and all those things need to sense some data, compute, analyze, and share the data with the cloud or with other smart devices. For this, if we have a look at smart devices are a sub-part of the cyber-physical systems. I would like here to give a kind of definition of those smart devices. They are devices with some sort of sensing mechanism inside. This is really the main characteristic of a smart device. And it can compute data, and also it is able to communicate via the internet or with other smart devices or to the cloud, and possibly without any human interaction, because you never know where is the smart device and how you can interact and use it. Specifically in our work, we would like to show why we need to have some systems that are autonomous in energy, because this is really useful to have some systems that can recover their energy from the environment. And we also need high security in those systems. Of course, different level of security is requested depending on the application, but most of the time high security is necessary. And today, what we see is that this Internet of Things and smart devices is one of the top 3 growth drivers of the semiconductor industry. All those smart devices have something specific. They are in a variable energy and applicative needs. First, there are many different applications, and those applications have very, very different variable energy needs. Also, they are in a changing environment, and as their main characteristic is to sense some data, sense something physical, this changing environment is impacting a lot the system and the smart device. We have variations in the energy harvesting, we have variations in the communication channel, in the sensing, in the images if you use some image, and also some variations in the security level that you need. So 2 slides here to show you the main challenges of those smart devices. So first, this is a really fragmented market. There are lots of attractive applications, but there is no killer application. We are not able today to say there is one killer application where all the market will go. So this is really difficult for us designers to design a single chip for one application, because this single chip will be specified for one application and not usable for another application. And also, if you want to be able to use those smart devices, then you need to have a strong co-design between software and hardware, and to cover each archetype of those smart devices. So where is the real value when you speak about IoT and smart devices? First, you need to provide a complete solution. If you do not provide a complete solution, you cannot use all the powerful IoT system. And also, you need to cover all the multiple layers of the technology stack, from hardware to software and up to the system and the network. And this is not easy, because we used to design some systems that are quite easy to program. And here, you also need to deploy it in a network, in a full network. Another challenge is security and privacy of user data. If you think to use IoT in the human body or something like this, then you really need to have a high security level, and you need to provide what we call an end-to-end security. This is a solution that covers the entire IoT stack, and this is really necessary because you do not want to have your data that are not protected and your data that are distributed in the cloud without any security. Another problem or challenge, I would say, is the standards. There are multiple competing standards in all the domains, in security, in communication, and specifically this graph here shows the communication standards. We have today a lot of standards, and they are all competing, you never know which will be the standard that will be used, and probably many standards will be used. And Caroline will show in the talk after me that those standards can be maybe managed together with some platforms that are flexible to communication standards. Also, something really interesting and mandatory is the low power consumption, and specifically the low energy. Every improvement that could be done in this domain, in low power, will be really mandatory and a great differentiator for your smart devices. And this is highly dependent on the application needs that you have. So it depends on which application you have. Maybe sometimes you will have a lot of energy, then you will be able to have, for example, a smart camera that will be able to provide nice pictures. But on the other hand, maybe you have some a simple monitoring system with a really few energy, and then in that case you will really need to save the energy. So usually, what is a smart device? A smart device, usually here I show a connected sensor node. There is some element for communication. It is radio here, some sensors, of course, because we are sensing some data. There is also a microcontroller subsystem in which you are computing the data, and there is a large part of the sensor that is power management and energy harvester or battery management. This is for power management to reduce the energy inside the node. If you consider this architecture, then this is not something flexible. This is something that is really fixed. And what we would like, if we consider the fragmented market that I have shown, the low power consumption and some adaptivity that is needed, then you can think about a system that is more partitioned. It is partitioned in a one part that is really low power. We are in the picowatt or microwatt area. And there is another part that is more the milliwatt area. You can think that you have a lot of energy that is recovered, and then you are able to do something that is more interesting. If we look at some applications, so here we have, for example, the camera, the secure communication, the data fusion, and the tracking and monitoring. You can have one application that is requiring different energy needs depending on what you do with this application. For example, tracking and monitoring, most of the time we need less than milliwatts. But for smart cameras, for example, if you need to have only one part of the image, then you can have something that is less consuming. But if you need to communicate something that is a nice picture with a lot of information inside, then you need to have a lot of energy. And we are in that part of the, sorry, the mouse is not visible. So you have a large part of the power that is consumed in that part. So what we propose, we have an architecture that is a partition architecture that we have called Elliott for low power IoT. And this is split into two main parts. The first part is a part that we call always responsive system. This is extremely low power, but with some really simple tasks. The tasks are just to send something that is simple, then communicate something that is simple. In terms of a radio, we have only wake-up radio. And then when we have enough energy that is recovered in the environment, or if we have enough energy, then we can open this platform to what we call the on-demand subsystem. On-demand subsystem is corresponding to a specific application, and depending on this application, we will develop this part of the platform accordingly. Of course, in terms of power consumption, the always responsive part is really low power, and the on-demand part can be less power consuming, but then it delivers all the application needs that we have. So if we look now at this architecture, so this is what we have called Elliott. On one part, we have the always responsive subsystem. This subsystem is energy conscious. It means that it is recording what is happening in terms of energy around the smart system. And then, in that case, if there is enough energy, then we can go and open and wake up the on-demand part that is fully applicative. So if we look at the responsive part, there are a lot of wake-up sources. Wake-up sources can come from sensors, but this is only wake-up. This is just maybe you cross the level of 100 Celsius for the temperature. We have wake-up radio. It means that we are just identifying something in the communication channel, but this is not a real communication. We have some wake-up on imagers. It means that we can maybe have a look on the picture and just see if the doors is opening in a room. And we have some timers. This is the classical timer wake-up. For this, we need some control. We have a lot of wake-up sources, and then we need some control. This is done by something that is asynchronous. It means that most of the time, this part is really in sleep mode, and once we have a wake-up interrupt, then the wake-up controller is reacting with the rest of the platform. For this, we also need to have some energy control. This energy control is able to control all the architecture according to the energy needs that we have. And of course, this part is also requiring a lot of security, because you do not want to have some security issue in a wake-up platform. Then, once we have a lot of energy and once the application is required, a specific application, we go to the on-demand platform. This platform is woken up according to the application and according to the energy. This is fully application-driven. It means that all the coprocessors and the processor that we have in this part are dedicated to a specific application. We can think about cryptography, data fusion imagers. And here we have a classical microcontroller that is, for example, an ARM M0+, M3, M4, it depends. And this part is also able to communicate in real communication all the data that we are computing. And there is, in this part, a lot of integrity and confidentiality, and we need a lot of cryptography here. Finally, if we want to integrate all this in one single chip with one platform, we need to have a global optimization of the system. This is where we will have a large gain in terms of energy if we are able to optimize the full system. For this, each block of the architecture should be able to be fully adaptive. Adaptive in terms of performance. It means that you can exchange some performances against some power, and then the block should be adaptive. For this, if it is adaptive, it has to be configured. So at the top of the architectures, of this architecture, we have power management, and we also have configuration management. And then, according to this configuration, we should be able to find the most energy efficient point of the architecture according to the energy available, the energy needs, and the application. So today, we will mainly focus on data computing. This is the next talk. On wireless communications, we have 2 talks this morning on wireless communications, and on power management, how to recover this energy, how to manage the power of the battery to be able to have a long lifetime of those smart devices.